What's up, everybody? Welcome back to yet another episode of Basic CHEM 101 with Sihlebonani. My name is Sihlebonani, and today we continue from last week. We did the wave nature of light. We are doing the particle nature of light. So let's get to it.
Let's go. This is for every child that wants to make it one day. Izimbo class and presence of mind is elsewhere. Swinga usudlani afuna kudledlale. Already alisibani and the timer is nowhere. I know your pain, you don't have to be scared. The dreams are very pure, they are written in focus. Keep that pen and paper, they will take you to that day. In the meantime, stand up, heavy.
Now, today, let's speak about light behaving as a particle, because light has a dual nature. Now let's imagine you have a very sensitive detector and you are trying to detect for light energy. So in your detector, let's say this is where you get. There are high chances that you would get nothing, and then at some point you get some energy. Then you get nothing, you get some energy. Get nothing, you get some energy. Nothing, energy. So there are high chances that your detector can detect some energy in small deposits. We can say light deposits discrete energy. So if light deposits discrete energy, at some point you get some energy, at some point you don't get anything. Now that discrete energy that is deposited by light is what is called your quanta. And if you want to increase this energy, the only way that you can increase is through the increase of the frequency of that particular light. So if the energy increases, your frequency would also increase, or if your frequency increases, your energy of this light, it also increases. So if the energy is directly proportional to the frequency of light, this is what a scientist called Planck came up with. So if there's a proportionality, you replace the proportionality by an equal sign and a constant. So in this case, that will be your Planck's constant. So the energy of light is equal to hv, which one? This one is your Planck constant, which is equal to 6.63 times 10 to the negative 34. So that is your Planck constant. So you can see that this value is very small. So sometimes if you don't have a very sensitive detector, you may not even be able to detect that there is energy that is deposited in discrete amounts. So from there, they say Einstein used that equation from Planck to explain the concept of a photoelectric effect. Now, a photoelectric effect is illustrated in, let's say you have let's say this is your metal. If you know, your metal has electrons on its surface. So if your metal has electrons on its surface and you shine light on it, now that we know light has energy, so if your light shines on a metal, what the metal does, it absorbs this energy from the light. Now, if it absorbs enough energy from this light, and then if the energy from the light is equal to the energy that can be absorbed by the metal, what happens next is that the light energy, after it has been absorbed and the metal cannot absorb anymore, now there is a collision of particles. It collides with these electrons. Then once it collides with one electron, now one electron can be ejected, or electrons can be ejected from the metal. So the amount of energy that is shined on the metal can determine the electrons that are ejected in the metal. It can also determine at which speed those electrons would move. So you have this light energy. It is absorbed by the metal, but once it can no longer absorb this energy from the light, electrons are ejected. So once electrons are ejected, they move. Once there is a movement, there is also kinetic energy of those electrons that are ejected from the metal. So since you know that there is a concept called the conservation of energy, you will also know that if there is energy that is coming in, there must be equal energy that is coming out. So which is your energy of the photons, which is this one. It must be equal to the energy that comes out, which is the final energy. Now, what happens here is that some of the energy is absorbed. Now, this energy that is absorbed by the metal is called your work function. Work function is usually denoted as this symbol. Then some of the energy is used by the electrons as kinetic energy when they are ejected, which is, we have your kinetic energy there. Now, work function, which is work function, is the minimum energy needed in order for electrons to be ejected. Now, each metal has its own work function. So a certain metal will have a work function of a certain value. And then your light will have its own energy. For an example, you will calculate light. Let's say your light has an energy of, which is your photon. You calculate using E is equal to HV. Your photon, let's say it has 30 joules, for an example. And then your metal has a work function of 50 joules. Now, in this case, if you calculate your energy, you get 30 joules, and then you calculate, or you know that your metal has a work function of 50 joules. The question would be, would there be electrons that are ejected? Because you know that the energy is first absorbed by the metal. So if this energy is less than the energy that can be absorbed by the metal, it means no electrons will be ejected from that particular metal. So what needs to happen for an electron to be ejected, this energy of your light or of your photons, it has to be larger than the work function of your metal so that electrons are ejected. Now, let's look at one example and then we call it a day. So your example would be, you have calcium with a work function of 4.34 times 10 to the negative 19 joules. And then you have a wavelength from the light, which is equal to 345 nanometers. So what we know here is that calcium can absorb this amount of energy before it ejects an electron. So the question is asking for the speed of an electron that is ejected. But for us, we'll take it step by step. First, we'll check if electrons can be ejected from here. So we'll have to calculate the energy of the photon, which is E is equal to hv. But here we have wavelength, not frequency. So in that case, we know that frequency is equal to speed of light divided by lambda. So from here we'll have c times c, h times c over lambda. Then that's 6.63 times 10 to the negative 34 times 3 times 10 to the power 8 meters per second. Then we divide this by lambda, which is 345 nanometers. Then you get your answer. But looking from this energy of the photons is greater than the energy of calcium. So from here, we can safely say that electrons will be ejected. So if electrons would be ejected, what is the speed of those electrons? So from what we had just spoken about, we know that energy of the photon is equal to work function plus kinetic energy, which is, we have this as 5.76 times 10 to the negative 19. Then we have this as 4.34 times 10 to the negative 19 plus kinetic energy is equal to half mv squared. Then we'll have this, or if you do your mathematics, you'd find that your v, which is velocity of your electrons, will be equal to 5.76 times 10 to the negative 19 minus 4.34 times 10 to the negative 19, all multiplied by 2 divided by mass of your electron then this is your square root, and your mass of your electron is equal to 9.11 times 10 to the negative 31 kg. And then you substitute this mass here, and then once you do that, you will get your velocity, which is equal to 5.59 times 10 to the power 5 meters per second. So that is calculations involving the photoelectric effect. And that is proof that light can behave as a particle. It can also behave as a wave from the last video that we did. So this was our proof, and I hope you understood what we are talking about. And if you got something out of this video, please press the like button. Also, don't forget to share. Also, tell your people to also subscribe and support us in moving forward. Thank you very much for watching. This has been Basic Chem 101 with Sihlebonani. My name is Sihlebonani, and thank you again for watching. See you on the next video. Booyah!